let's say you've been given a sequence, for example, this one here. As it turns out, this one's quite straightforward, but in the future, it will be a lot more complicated. But let's say you've been given a sequence. There are times when you want to understand this sequence. For example, as n tends to infinity, where will this head towards? Meaning, what would be the limit of this sequence? Or will this sequence always increase, or will it always decrease, or will it stay all the same? So in this example, it happens to be a straightforward sequence, but in the future, this will be very, very complicated, and it would be hard to determine whether or not this will head towards a limit, or whether it will increase or it will decrease, and so on. So the way we would understand this sequence would be to use this trick. We would so we've been given a sequence. We've been given this sequence here. We would turn this sequence into a function. So we would map a function on top of the sequence. So this function here can generate the sequence here. So for example, when looking at the function, when x equals 1, you put into here and it will jump to your first sequence. It will jump to the 3. When x equals 2, put it into here, and then it will jump to your second term, and so on. When x is 3, put it into here, and then it will jump to your third term. So the point here is that to understand something complicated in the future, we would turn this into a function, and then make use of our knowledge of functions to work backwards and understand the sequence. So in the future, you would be given something very complicated, turn into a function. Once it's in a function, we know a lot about functions. So we would use our knowledge of functions to understand, well, to basically work backwards and understand the sequence. So for example, hang on. So for example, if you've been given a sequence and it generates this here, and let's say this heads towards some sort of limit. So which it is in this case here, it is heading. If you look at this sequence here, it is heading towards a limit. It is heading towards, well, the limit here is 2. It's heading towards 2. As n increases from 1 to infinity, the sequence is heading towards 2. So we would write it as this. So suppose you have something that generates this sequence here. If this sequence is heading to some sort of limit, we would write it as this. So this thing here is really saying this is your sequence here. As n increases, as n heads towards infinity, as n heads towards infinity, the sequence, the one term here, this one term here is heading towards a limit. In our example here, the limit is 2. In our example here, the limit is 2. But the point is that suppose you have a sequence here and it generates this sequence here. As n heads towards infinity, then this one particular term here is heading towards this limit here. Okay, so this really describes it describes a sequence. So hang on. So if you have a function, and you know this function heads towards some sort of limit, then your sequence will also head towards that limit. So when you see this here, this is your function. So when you see this in your mind, you should visualize the function itself, the continuous smooth function. So when you see this in your mind, you should visualize a graph. You should visualize a line. But then when you see this is your sequence, because this is your sequence. So when you see this in your mind, you should be visualizing this. You should be visualizing this. It's just you see this thing here. This thing here is continuous. This thing here is your actual function. This thing here is your actual function, but then this thing here is your sequence. So when you see this in your mind, you should just be visualizing this. You should just be visualizing these dots here, because when it comes to sequences, 1.7 is meaningless. Anything in between here is meaningless. When it comes to sequences, you're only concerned with integers, positive integers here. It's meaningless to have 5.7. Around here it's just meaningless. So when you see this, hang on. So when you see this, in your mind you should visualize the function. Now what it's saying here is that what it's saying is that, hang on, what it's saying is that if you have a sequence, turn it into a function. Now once you've turned this into a function, any point on this line will be on the function. Any term on the sequence will be on a function, and if the function converges to some sort of limit, then the sequence will have no choice but to also converge to that same limit, because every term in the sequence maps on top of the line, on top of the function. So the function heads towards some sort of limit, then the sequence will also head towards the same limit. So what this is saying is that, hang on, what this is saying is that, well, what this is saying is that if your function heads towards some sort of limit, then your sequence will have no choice but to also head towards the very same limit. So when you see this, in your mind visualize the function. When you see this, in your mind visualize these dots. Well, if this function heads towards some sort of limit, then your sequence will also head towards the same limit. So whenever this is true, then it will automatically imply that this will be true. But by the way, going backwards will not be true. So for example, hang on. For example, hang on. So for example, you going backwards. So suppose your sequence is heading towards some sort of limit, then it doesn't necessarily mean that your function will head towards that same limit. For example, hang on. So for example, let's say you've got a sequence that's heading towards a limit, like in this case here. This sequence here, it is heading towards a 2. But then a function, well, you could have a function looking something like this. You could have a function looking something like this. You see, this function could head towards somewhere else, but then the sequence could head towards a limit, but the function, well, what I'm trying to say here is that this, if this is true, then it will automatically imply that this will be true. But then going the other way would not necessarily be true because of this. Because here you can see that the limit, let's say the limit here converges to 2 in this case. In this case here is converging to 2. But then there exists a function that could be something like this. So the point here is that if this is true, then this must be true. Okay, but going backwards might not be true. Okay.